Hello and welcome to Video Podcast 10.2. In this vodcast, I will overview coastal upwelling and deep ocean circulation. Our previous vodcast overviewed surface currents, which are driven by the prevailing winds. But winds can also cause vertical water movement. Upwelling, which is the rising of cold deep water to replace warm surface water, is a common wind-induced vertical movement of water. Coastal upwelling occurs on the west coast of continents, in places like California, western South America, and West Africa, to name a few. Coastal upwelling occurs in these areas when winds blow towards the equator, parallel to the shoreline. A combination of coastal winds and the Coriolis effect cause surface water to move away from the shore. As a result, deeper ocean water upwells, or rises to the surface, to replace the water that was pushed away from the shoreline. At this point, I'll explain the process of coastal upwelling by referring to some images. In this first image, let's consider the prevailing winds that affect southern Africa. Specifically, the southeast trade winds blow roughly parallel to the shoreline. This results in surface waters being pushed north towards the equator. Now that we've considered the prevailing winds that affect southern Africa, let's consider the ocean currents in that area. The primary ocean current that affects the southeast coast of Africa is the Benguela current, and it's a cold water current that works its way north towards the equator. Because we're considering the southern hemisphere, the Benguela current will deflect left due to the Coriolis effect. Because the Benguela current is moving north and away from the coastline, it's essentially pulling water away from the African continent. As a result, deeper water will upwell off the western coast of Africa. The color-coded image shown provides strong photographic proof of coastal upwelling. Upwelling brings significant amounts of dissolved nutrients like phosphates and nitrates to the surface. These nutrients are essential for plankton, and plankton support extensive populations of fish and other organisms. In this color-coded image, the red and yellow correspond to really high concentrations of chlorophyll, and high chlorophyll concentrations indicate high amounts of photosynthesis. All of this photosynthesis is heavily reliant on the upwelling of nutrient-rich water from deep in the ocean. I'll now turn my attention to deep ocean circulation. Deep ocean circulation is a response to density differences among water masses. Denser water masses sink and spread out beneath the ocean surface. As overviewed in a previous vodcast, density differences in water are a function of both temperature and salinity. And because water density depends on both temperature and salinity, we sometimes refer to deep ocean circulation as thermohaline circulation. Don't let the word thermohaline scare you. Thermo means heat and haline means salt. Just to refresh your memory, cold water is more dense than warm water, and high salinity water is more dense than low salinity water. Therefore, really cold, really salty water will be really dense water. Shown on this slide is an image of what's sometimes referred to as the ocean conveyor belt. This simple model of ocean circulation tracks the movement of water around planet Earth. To understand how this conveyor belt model works, let's start in the high latitude regions near the surface. When sea ice forms, the salinity of the surrounding water will increase because the salt is left behind when ice forms. This high salinity water is now more dense, so it will sink. As this water travels the deep ocean, its density remains essentially unchanged. Deep water near Antarctica is some of the densest water in the world. It moves very sluggishly in the deep ocean, and it can take thousands of years to emerge back at the surface. Eventually, the deep waters will upwell and continue moving through the circuit. So to summarize it as simply as possible, warm water moves poleward, it sinks, and then eventually upwells to complete the circuit. Okay, that concludes this video podcast. In our next vodcast, I will overview ocean waves.